friends, welcome to this lecture. In this lecture we will continue our study of existence and uniqueness theorem of for dynamical system. So, if you recall in previous lecture we have discussed this initial value problem that y dash equal to f t y, y t naught equal to y naught. We are discussing the existence condition on f such that this initial value problem has a solution, and not only solution, it has a unique solution. So, what we have done, we have shown that this initial value problem is equivalent to an integral equation, that is y t equal to y naught plus t naught to t f of s y of s here, and then with the help of this integral equation we have defined the sequence of approximation solution, that is y n plus 1 t equal to y naught plus t naught to t f of s y n s ds for n equal to 0, 1 and so on. So, once we have this sequence y n, then we try to find out whether this will converge to some solution or not. For that we need some additional condition on f t y. One such condition is the the Lipschitz condition, and we have shown that f satisfy the Lipschitz condition if it satisfy the following condition, that is f t comma y 2 minus f t y 1 is less than or equal to k times modulus of y 2 minus y 1, and here this t and y belonging to some closed rectangle R, and it is defined like this. And we have shown that if double f double y is continuous and defined on this closed rectangle R, then f already satisfying the Lipschitz condition. That is the content of the previous lecture. Now, in this lecture we try to show that this y n is converging under the condition that f satisfy the Lipschitz condition, or double f by double y is continuous on this rectangle R, and not only it will converge to a solution y t, which is the solution of this initial value problem. That is the content of this lecture. So, here let us move. So, before we do anything with these successive approximation, we try to show that they are defined properly, in the sense that all these approximating solution belongs to that rectangle R here. So, it means that we must first know that the point s comma y j s remains in the rectangle R for every s in the in the interval I. Here I is defined as t naught to say t naught plus. Now, that is the content of this lemma 4. Choose any two positive numbers a and b, and let define R as t y belongs to R 2, t is lying between t naught to t naught plus a, comma y minus y naught modulus of y minus y naught is less than or equal to b, be the rectangle. This is the rectangle we have defined, and we assume that f is continuous on this rectangle R. So, it means that it is bounded, and let us define m as the maximum value of y belongs to R modulus of f t y, and then we can find out the quantity h, that is minimum of a comma b by m. So, then we say that modulus of y n t minus y naught is less than or equal to m t minus t naught for all t lying between t naught to t naught plus h. So, this lemma says that all the approximating sequence y n t satisfy this condition 13, and this means that it belonging to rectangle R. How we can say that? Since t minus t naught is bounded by h, so we can say that y n t minus y naught is less than or equal to m, and t minus t naught is lying in say in h. So, we can say m of h, and h is what? Minimum of a comma b by m. So, we can say that it is writing as in this. So, it means that y n t minus y naught is less than or equal to b. It means that all these y n t belongs to this rectangle R here. So, what this lemma says that the graph of y n t is sandwiched between the lines y equal to y naught minus m t minus t naught and y equal to y naught plus m t minus t naught for t lying between t naught to t naught plus h, and these lines leave the rectangle R at t equal to t naught plus a if a is less than b by m, and t naught plus b by m if b by m is less than a. Now, so it means that the graph of y n t is contained in R for all t between t naught to t naught plus h. So, let us try to prove this lemma, and the proof of this lemma is given with the help of mathematical induction, and we say that that this is obviously true if n equal to 0. So, it means that for n equal to 0 you can simply say that this is modulus of y 0 minus y 0. So, this is automatically less than this quantity. So, next we assume that 13 is true for n equal to j, and we try to show that it is also true for n equal to j plus 1. So, it means that we assume that yjt minus y naught is less than or equal to mt minus t naught. It means that this yjt belongs to the rectangle R. Now, try to find out modulus of yj plus 1 t minus y naught, and we can say that this can be written as t naught to t f of s comma yjs d of s. Now, since yjs belongs to rectangle R, so it means that s yjs is an element of rectangle R. So, it means, and we already know that f is bounded on that rectangle by capital M. So, we can say that this modulus of t naught to t f of s yjs ds is further less than or equal to t naught to t modulus of f of s yjs ds. Now, this is bounded by capital M. So, we can write down that this is bounded by m into t minus t naught. So, it means that yj plus 1 modulus of yj plus 1 t minus y naught is bounded by m t minus t naught. So, it means that it satisfies the condition we have assumed. So, it means that this 13 is true for all n from 0, 1, 2 and so on. So, and this shows that all these t, y and t belongs to the rectangle R. So, it means it is properly defined. Now, let us move to the convergence of this y and t. So, convergence of y and t, and to show this that Picard iterates y and t, we call this y and t as Picard iteration or Picard iterate, and we show that this converges if this del f by del y exists and is continuous, or that f satisfy the Lipschitz condition, and we have shown that if this exists and continuous, then it automatically satisfy the Lipschitz condition. Our first step is to reduce the problem of showing that the sequence of function y and t converged to a quite simpler problem of proving that infinite series converges. So, here these two problems is equivalent if we can show that y and t can be written as following manner, and this is not very difficult to visualize, that y and t can be written as y naught plus y1 minus y naught plus so on yn minus yn minus t. If we look at, then these will cancel out each other and we will have y and t. So, we rewrite y and t as this partial sum, that is y naught t plus y1 t minus y naught t plus so on, and we say that limit n tending to infinity y and t will be what? This is nothing but y naught t plus y1 t minus y naught t, and this goes on. So, it means that this limit exists provided that this infinite series is basically convergent series, and we can summarize this as writing that this implies what? That summation, I can write it yi minus yi minus 1 t I equal to, say here it is 0 to in fact it is 1 to n y naught here, and then we are looking at limit n tending to infinity. So, this is limit n tending to infinity y and t is basically this. So, we to show that this limit exists provided that this limit exists, and this limit means this limit is less than infinity. So, our aim is to show that this infinite series basically converge. So, this is done in the following manner. So, let us look at y n t minus y n minus 1 t. So, here we try to show that this quantity, let us look at this quantity, and y n modulus of y n t minus y n minus t, and we already know that y n t is given by Picard iteration. So, it satisfies. So, y n t is basically what? Y n t is basically y naught plus t naught to t f of s y n minus 1 s ds. So, using this expression of for y n t and y n minus 1 t, we can write down this as modulus of y n t minus y n minus 1 t equal to t naught to t f of s y n minus 1 s minus f of s y n minus 2 s ds. this can be further less than or equal to T naught to T modulus of f of s y n minus 1 s minus f of s y n minus 2 s ds. Now here either you use that del over f by del over y exist and continuous on the rectangle R, or you simply use that f satisfy the Lipschitz condition. In both way you can say that this is further less than or equal to k times y n minus 1 s minus y n minus 2 s ds. So, this quantity is less than this quantity, and we can get this thing modulus of y n t minus y n minus 1 t less than or equal to k times T naught to T modulus of y n minus 1 s minus y n minus 2 s ds, where t is lying between T naught to T naught plus h. So, here we have a recurrence relation between y n minus 1 t. So, you can use this 16 repeatedly and we can get the bound for this this quantity, this infinite series. So, let us look at n equal to 2. For n equal to 2 we can write y 2 t minus y 1 t less than or equal to k times T naught to T y 1 minus y naught ds. Now, this quantity we have already obtained using lemma. This can be written as m times t minus T naught. Now, here it is, I can write it s minus T naught. Here we are using this lemma that y n t minus y naught is less than or equal to m t minus T naught. This is true for n equal to 0 onward. So, we can write it n equal to 1 here. So, modulus of y 1 t minus y naught t is less than or equal to m times t minus T naught. So, using this we can write it here and we can say that it is less than or equal to k times m T naught to T s minus T naught ds, and when we simplify we have this thing. So, for n equal to 2 modulus of y 2 t minus y 1 t is less than or equal to k m times T minus T naught whole square upon 2. Similarly, for n equal to 3 we can write a modulus of y 3 t minus y 2 t is less than or equal to k times T naught to T y 2 modulus of y 2 s minus y 1 s ds, and for this we have already obtained and we can plug in this value and we can have this. So, by induction we can say that we have this estimate that is modulus of y n t minus y n minus 1 t is less than or equal to m k n minus 1 m k to power n minus 1 t minus T naught to power n divided by factorial n for t lying between T naught to T naught plus h. So, so once we have bound for this, now let us look at this y 1 minus y naught plus y 2 minus y 1 and so on. So, this term is bounded by this, second term is bounded by this and so on. Now, so it means that this series is bounded by this is infinite series. Now, t minus T naught is bounded by h. We have already assumed that t is lying between T naught to T naught plus h. So, t minus T naught is bounded by h. So, we can replace this, we can look at the upper bound. So, m h plus m k h square upon factorial 2 and so on. Now, here we just do some more simplification, we divide by k and multiply by k. So, we can write m by k, kh plus kh square upon factorial 2 and so on. And if you look at this, this can be simplified in this manner that we can write it m by k. This thing is nothing but infinite series e to power kh minus 1, and we can say that since it is a converging series, so it means that this quantity is less than infinity. So, it means that this infinite series is bounded by infinity. So, if this infinite series is bounded by infinity, so if we add by y naught, we say that it is still less than infinity. So, it means that our series is absolutely convergent. So, it means that not only it is convergent, it is absolutely convergent. So, here we can say that this series is absolutely convergent, what we have shown here. So, if it is convergent, let us find the limit say y t, and this convergent for some t lying between T naught to T naught plus h. Now, let us find out the limit y t and we try to show that this limit is the required solution. So, we will try to show that y t satisfies the initial value problem, this y t equal to y naught plus T naught to T f of s y s ds, and y t is continuous, because we have shown that if a y is a continuous solution of this, then y satisfy the initial value problem. So, we have to show y is continuous and y satisfy the initial value problem integral equation given by this. So, so first we show that it satisfies the integral equation. For that, recall that y n plus 1 t equal to y naught plus T naught to T f of s y n s ds. Now, take the limit on both sides, we have limit n tending to infinity y n plus 1 t, that is given as y t equal to y naught plus limit n tending to infinity t naught to t f of s y n s ds. So, what we want to show is that this quantity is nothing but t naught to t f of s y of s. So, this we want to show. It means that this limit can go inside the integral and inside your f also. So, it means that if this is equal to this, it means that we want to show that t naught to t f of s y s ds minus t naught to t f of s y n s ds is tending to 0 as n tending to infinity. So, this can be rewritten in this way, that as n tending to infinity, this quantity is tending to this limit. To prove this, we first observe that y t lies in R, because each y and t lies in R. So, its limit will also belongs to this in rectangular. You can see like this, y in t minus y naught less than or equal to m t minus t naught. Let us take the limit inside, limit n tending to infinity. It is independent of n, so no problem, and since modulus is a continuous function, you can write it that y t minus y naught is less than or equal to m t minus t naught. So, it means that y t belongs to the rectangle R. So, it means that t y t belongs to R. So, that is what we want to do. So, once it is done, look at this quantity modulus of t naught to t f of s y s ds minus t naught to t f of s y n s ds, and this further less than or equal to t naught to t f of s y s ds minus f s y n s ds. Now, using Lipschitz condition, or say that w f by w y is continuous, we can write it as this mod less than or equal to k times t naught to t y s minus y s ds. So, if we can find out the bound of this, then we can talk about this quantity. So, y s is basically what? Y s is y naught plus j equal to 1 to infinity modulus of y j s minus y j minus 1 s, and y n s is y naught plus j equal to 1 to n y j s minus y j minus 1 s. So, using this, find out modulus of y s minus y n minus 1 s, and we can write in this quantity that modulus of y s minus y n s is equal to j equal to n plus 1 to infinity y j s minus y j minus 1 s. Now, we already have found the bound of this y j s minus y j minus 1 s. So, using the bound here, we can write down that y s minus y n s, in fact, we have find the bound of y j modulus of y j s minus y j minus 1 s. This bound we have obtained in basically here in equation number 18 basically. So, we have bound the bound of this modulus of y n t minus y n minus t as m k n minus 1 t minus t naught to power n divided by factor n. So, using this, we can write down modulus of y s minus y n s is less than or equal to m times j equal to n plus 1 to infinity k to power j minus 1 s minus t naught to power j divided by factorial j. Now, here again this s minus t naught is bounded by h, and we can further simplify and we can write down this is m by k j equal to n plus 1 to infinity k h to power j upon factorial j. Now, if you look at this is the tail of e to power k h. Now, if it is a converging series, then tail is tending to 0 as n tending to infinity. So, it means that y s modulus of y s minus y n s is tending to 0 as n tending to infinity. So, it means that modulus of j naught to t f of s y s ds minus t naught to t f of s y n s ds is less than or equal to m times j equal to n plus 1 to infinity k h power j upon factorial j t naught to t ds. So, and this can be written as bounded by h here, and as we pointed out that this tail is tending to 0 as n tending to infinity, then this quantity is tending to 0 as n tending to infinity, and this implies that limit n tending to infinity t naught to t f of s y n s ds is equal to t naught to t f of s y s ds, and this implies that y t satisfy the equation number 18, that is y t can be written as y naught plus t naught to t f of s y of s ds. Now, only thing we have to prove now is that y is a continuous function, because when y is continuous solution of this integral equation, then y is a solution of initial value problem. So, to show that y t is continuous, we can use the Weierstrass M test, and we can say that if you look at this quantity j equal to 0 to infinity yj plus 1 t minus yj t uniformly converges on this interval t naught to t naught plus h. So, how we say that it is uniformly convergence? Again look at your equation number 18, 18 is given by this. So, if you call this as say Mn, and we already know that summation Mn is basically less than infinity. So, it means that summation yn t minus yn minus 1 t is converging uniformly. So, this is Weierstrass Mn test, that if yn t minus yn minus t is bounded by Mn and summation Mn is less than infinity, then this infinite series is uniformly convergent. So, using this we can simply say that this convergence is uniform. So, this implies that in the view of this definition, that this limit infinite series j equal to 0 to infinity yj plus 1 t minus yj t is converging absolutely and uniformly in the interval t naught to t naught plus h. And we already know that yj t is given as this, and this implies that yg t is a continuous function and yj t is converging to yt, and this convergence is uniform. So, the limit will also be continuous. So, yj t is continuous implies that yt is continuous, because your convergence is uniform. So, it means that therefore, the limit function yt is a continuous function. So, now we have shown that the limit function is a continuous function and it satisfies the initial integral equation. So, it means that it is also the solution of the initial value problem, that is what we wanted to show here. So, if we summarize, we have proved the following theorem: let f and dever f by dever y be continuous in the rectangle R, and rectangle R is defined like this, that t is lying between t naught to t naught plus h modulus, and y minus y naught is bounded by b, and m is given by minimum of a comma b by m. Then the initial value problem, y dash equal to f t y comma y t naught equal to y naught has at least one solution y t on an interval t naught to t naught plus h. Here h is what? H is minimum of a and b by m, where m is the bond of f t y. So, here we say that similarly we can prove that this similar kind of result is also true for t less than or equal to t naught. And now we want to show that not only this, it has a unique solution. So, how we show that it has a unique solution? In fact, this theorem is given for this condition that f and dever f by dever y be continuous, but we have already shown that dever f by dever y continuous in this rectangle R implies the ellipsis condition, and we have proved the theorem for ellipsis condition only. So, we can say that let f is continuous and satisfy the ellipsis condition, then it has a solution in this interval t naught to t naught plus h, where h is minimum of a comma b by m. Now, let us prove the uniqueness of the solution. So, the previous theorem guarantees the existence of at least one solution of this y dash equal to f t y, y t naught equal to y naught. So, one solution is guaranteed. Let us assume that we have two solutions, let us say z t and y t. So, y t satisfy this, z t will satisfy this. So, we want to show that y t is ideally equal to z of t. So, for that let us consider modulus of y t minus z t, then it is bounded by k times t naught to t modulus of y s minus z of s ds. Now, we want to claim that y t minus z t is ideally equal to 0, that is y t equal to z t. So, for that we use the following lemma, that let w t is non-negative for every t with satisfying the condition integral inequality, that is w t is less than or equal to k times t naught to t w s ds, then w t is ideally equal to 0 here. So, using this we try to prove our result. So, first let us prove this lemma and then we will use it. So, we cannot directly differentiate this. So, what we try to do here, let us assume this quantity as say us. So, let us say ut as t naught to t ws ds. So, ut is given here, then we can differentiate this and we can write du by dt as wt. So, we already know wt is less than or equal to k times t naught to t ws ds and this thing. So, now, but this is what? This is your ut. So, we can write du by dt as less than or equal to k times ut. So, du by dt minus k of ut is less than or equal to 0 basically. Now, this can be written as using integrating factor. I can rewrite this as d by dt of e to the power minus kt ut is less than or equal to 0. Now, integrate between t naught to t and we can write down this thing that e to the power minus k t minus t naught ut is less than or equal to ut naught. That we have to integrate between t naught to t and we can say whether it is true or not. Then we have this e to the power minus k times t minus t naught ut less than or equal to ut naught. Now, what is ut naught? Ut naught you can check from this that it is coming out to be 0. So, it means that e to the power minus k times t minus t naught ut is less than or equal to 0. This quantity is always non-negative. So, it means that ut is less than or equal to 0, but ut is already greater than or equal to 0 because this ws is non-negative, integrand t naught to t is positive. So, ut is greater than or equal to 0 and this shows that ut is less than or equal to 0. This is possible only when ut is equal to 0. So, it means that if ut is equal to 0, then you can put it here and you can say that t naught to t ws ds is equal to 0. So, it means that this is so 0 less than or equal to wt less than or equal to k times t naught to t ws ds. This quantity is 0. So, it means that wt is equal to 0. So, this shows the proof of this lemma. Now, using this proof of this lemma, we want to show that a solution is unique. So, here we assume that wt is equal to modulus of yt minus zt. So, when we assume this, then wt is non-negative, then this wt satisfy this quantity wt is less than or equal to k times t naught to t ws ds. And just now we have proved that if wt is non-negative and wt is non-negative and satisfying this inequality, then wt is 0. So, it means that this implies that this is equal to 0 and this implies that yt is equal to zt, and that proves the uniqueness of the result. So, it means that not only it has a solution, it has a unique solution. Now, let us summarize whatever we have done so far. So, here we have considered this initial value problem, that is dy by dt equal to f t y, yt naught equal to y naught, where f is a given function of t and y defined and continuous in some neighborhood of the point t naught comma y naught. We define the sequence of associated approximating solution as follows: yt naught equal to y naught, yj plus 1 t equal to y naught plus t naught to t f of s yjs ds j from 0 1 2 3 and so on. Then existence and uniqueness theorem is given as follows, that if f t y is a continuous function of t and y in a closed and bounded rectangle R and satisfy the ellipsis condition in R, then the successive approximation yj we have defined in this equation number 26 converges uniformly on the interval j in this interval j, that is t is lying between t naught to t naught plus alpha. In fact, we can prove the other way around also, that is modulus of t minus t naught is less than or equal to alpha to a solution y of the differential equation 24 that satisfy the initial condition 25. So, we have proved the existence and uniqueness theorem. Let us consider one simple example based on this. Consider y dash equal to t times 1 plus y with the initial condition y 0 equal to minus 1. So, here we can check, consider a rectangle R which consists this initial condition, that is 0 and minus 1. So, we have this rectangle centered at 0 and minus 1. So, that is R, and let f t y is equal to t times 1 plus y, and we can easily check that this satisfies the ellipsis condition, that is modulus of f t y 1 minus f t y 2 is equal to modulus of t times y 1 minus y 2, and we can say that if t modulus of t is bounded by a, so this is bounded by a times y 1 minus y 2. So, it satisfies the ellipsis condition with the ellipsis constant a here. So, it means that here by existence and uniqueness theorem, this problem has a unique solution, and here we can easily observe that this yt equal to minus 1 satisfy the initial condition as well as the differential equation. So, it means that since we have a unique solution and we already know that yt equal to minus 1 is satisfying the initial condition as well as the differential equation. So, it means that it is the only solution of the differential equation 27. So, it means that this problem has, since it has a unique solution and y t equal to -1 satisfy the initial condition as well as the differential equation, this is the only solution available for this differential equation. So, this initial value problem has the unique solution, that is y t equal to -1. So, now let us consider one more example and show that in this example show that the solution y t of the initial value problem y dash equal to e to power minus t square plus y square with y 0 equal to 1 exists in the said interval. So, for that let us consider a rectangle R, that is t lying between 0 to this root 2 upon 1 plus root 2 whole square y minus 1 less than or equal to b. So, only thing is that here we consider rectangle centered at 0 and 1. So, that is what we have considered here. Then we can since it is a closed rectangle, we can find out the bound of f t y. Here f t y is e to power minus t square plus y square. So, we can find out the bound of this. So, maximum of t y belongs to R e to power minus t square plus y square. This quantity is bounded by 1 because t is lying between this 0 to this. So, it is bounded by 1 and y is bounded by b plus 1, that we can easily check. Y minus 1 is bounded by minus b and b, and so y is bounded by 1 plus b. So, y is bounded by 1 plus b. So, y square is bounded by b plus 1 whole square. So, m is already obtained. So, we have already shown that this f t y is this, and we can easily check that del f by del y exist and continuous in this rectangle R. So, existence and uniqueness theorem, exemptions of existence and uniqueness theorem verified, and solution exists in an interval between t naught to t naught plus h. Here t naught is 0 here, and h is given by minimum of a is given by this and b by m. M is we have already calculated as 1 plus b plus 1 whole square. So, it means that solution exists in this interval t lying between 0 to minimum of this quantity. So, here this is some already number, given number. We want to look at that how much. So, it means that what is the value of this b. So, here b is an arbitrary value here. So, we can say that the largest h that can achieve is the maximum value of the function, this b upon 1 plus b plus 1 whole square. And so, let us to find out the maximum value of this, let us consider g b as b upon 1 plus b plus 1 whole square. To maximize this, let us consider g dash b, and you can say that 1 plus b plus 1 whole square. So, 1 plus b plus 1 whole square, sorry, this can be written as minus of this. Okay, let us. So, we can write it here. So, here we can write it b times 2b plus 1 minus this is what is your b. So, here we simply write b plus 1 whole square and this is equal to 0. So, g dash b equal to 0. So, this implies that you simplify it 2b square plus 2b minus b square minus 1 minus 2b. This is 0 because here numerator is so this can be written as b square equal to 1. So, it is b equal to sorry, it is something. So, to find out the maximum value of this g b, we need to find out b for which g dash b equal to 0. For that, let us calculate this. Here is square whole square, and this is 1 plus b plus 1 whole square and minus here b, and this is what 2 b plus 1 here, and this is equal to 0. So, here we want to show this is what 1 plus 2 b square plus 1 plus 2 b minus 2 b square minus 2 b equal to 0. So, here if you simplify, this can be cancelled out. So, we have 2 minus b square equal to 0. So, we have b as plus minus root 2. Now, b is a positive value. So, we have to take b equal to root 2. So, it means that this can be maximized if we take b equal to root 2, that you can check that g double dash b is negative for this value. So, here we can say that the maximum value of b upon 1 plus b plus 1 whole square is achieved for b equal to root 2. If we put b equal to root 2, we can have that the maximum value of this quantity is given by root 2 upon 1 plus root 2 whole square. So, it means that this proves that the solution of this initial value problem exists in this interval, that is t belong from 0 to root 2 upon 1 plus root 2 whole square. That is what we have shown here. So, what we have shown one example where we shown that solution exists in a particular interval. Now, suppose consider a region D, not necessarily a rectangle. The function f satisfies ellipsis continuity in y. Then given any point t naught y naught in D, we can always construct a rectangle R lying entirely in D with center at t naught comma y naught, and this hypothesis of existence and uniqueness theorem are then true in R, and we can apply our existence and uniqueness theorem to find out the solution of y dash equal to f t y satisfying the initial condition, and we can say that solution exists. But here we want to observe one thing, that in fact it may happen that a solution may exist on a larger interval than the one constructed in the proof of theorem 1. So, it means that it may happen that solution actually exists in a larger interval, but this existence and uniqueness theorem gives a smaller interval. For example, consider this example. Consider the following initial value problem: y dash equal to y square with y naught equal to 2. The solution is given by y t equal to 2 upon 1 minus 2 t. This we can simply solve because it is separation variable form, and we can say that solution exists in this entire interval minus infinity to 1 by 2. But if we try to solve this using existence and uniqueness theorem, we construct a rectangle R, that is modulus of t is less than or equal to a, y minus 2 is less than or equal to b. We can easily calculate maximum value of f t y, that is y square is 2 plus b whole square, and we can calculate the h alpha, that is minimum of a comma b by m, that is b upon 2 plus b whole square, and you can calculate the maximum value, and it is coming out that this maximum value is coming out to be 1 by 8. So, we can say that the if we apply existence and uniqueness theorem, I am leaving it to you how to find out the maximum value. You call it some h of some say h1 of b, and find out the value for which h1 dash b is 0 and h1 double dash b is negative, and you can say that that b is coming out to be 2 basically. So, you can say that maximum value is coming out to be 2. So, it means that by existence and uniqueness theorem, our solution exists in the interval, that is between 0 to 1 by 8. So, it means that here we can say that the theorem 1 gives the assurance of a unique solution in interval modulus of t less than 1 by 8, but we have already shown that this actual solution exists in a larger interval, that is minus infinity to 1 by 2 here. So, it means that this theorem is a local existence theorem. It means that this gives the existence in a small neighborhood of the initial condition, that is discuss the existence only in a small neighborhood of a initial point. So, first is very important thing, that it is a local existence theorem, and the proof of the above theorem required the ellipsis continuity of the nonlinear function even when we need only existence. So, it means that even when we need only half part, that is existence, then also this theorem requires the ellipsis continuity. Now, regarding the existence of a solution of 24, theorem 1 is not the only one best result. So, it means that if we want only the half part, that is we are interested only in the existence of a solution part, then this theorem is demanding much, because it is asking for ellipsis continuity and it is much more than continuity. So, here we have a one more result which gives only existence, may not give the information about the uniqueness, and that is your theorem 2. And suppose f is continuous on the rectangle R and suppose that this modulus of f t y is bounded by m for all points t y in this rectangle R, and alpha be the smaller of the positive number a and b by m, then there is a solution y of the differential equation that satisfy the initial condition existing on the interval t minus t naught less than or equal to alpha. If you look at the theorem 2, the only part missing is the ellipsis continuity, rest everything is same. So, it means that if we leave this part ellipsis continuity, still we can guarantee the existence of solution. Of course, the proof of this theorem 2 is not the same as we have discussed the proof of theorem 1, because in theorem 1 when we prove the convergence using the ellipsis continuity. So, the proof of this theorem 2 is not the same as we have done. I am not giving the proof of this, but just give one example based on this example. So, consider the equation y dash equal to 3 y to power 2 by 3 y 0 equal to 0. Here f t y is y to power 2 by 3, we can easily check that it does not satisfy the ellipsis condition. So, that we can check. So, it means that we cannot apply the previous theorem and we simply say that it has no solution, or we cannot apply this theorem to find out whether it has a solution or not, but we can check that it has a solution. In fact, not only one solution, it has infinite many solution, and that we can done by separation and variable thing, and we can say that if we define our solution properly, like y c t equal to 0 between minus infinity to c and t minus c cube when t lying between c to infinity, then this is a solution of y dash equal to 3 y to power 2 by 3 passing through 0 comma 0, and you keep on changing your c and we have different infinite many solution of this. So, c belonging to R and we have infinite many solution of this particular problem. So, here this f t y does not satisfy the ellipsis condition, still it has a solution, not only one solution, it has infinite many solution. So, this we can get it from the previous theorem, that if f is continuous on the rectangle R and f t y is bounded by m and alpha be the smaller amount of a and b by m, then this differential equation has a solution lying in this interval modulus of t minus t naught less than or equal to alpha. So, this example shows that even f t y is not satisfying the ellipsis condition, but is continuous and bounded in the rectangle R, then also it has a solution. It may not be unique solution that we have shown, because this problem has a infinite many solution here. So, this here existence is given by theorem 2, not by theorem 1, because theorem 1 is not applicable here. Now, one more corollary, because here we are missing the uniqueness part. For that we consider the following corollary, that if in addition to the assumption of theorem 2, the function f is monotonically non-increasing in y for each fixed t on R, then the initial value problem, this has a unique solution. So, it means that if we lose the ellipsis continuity and we consider only continuity, and if in addition if we assume that f is monotonically non-increasing in y, then we have existence and uniqueness together. So, here we are not providing the proof of theorem 2 and this corollary 11, but we simply we observe this thing, that in this course we will not prove theorem 2 or its corollary 11. Rather, we note down one point, that it is not possible to prove the theorem 2 by the method of successive approximation. So, the proof of theorem 2 and corollary 11 is not depending on the successive approximation. And one more example we can consider, that hypothesis of theorem 2 does not guarantee uniqueness of the solution. So, example is this, f t y is defined in this manner, and here we say that f is continuous and bounded by the constant 2 on D, that I am leaving it to you, that you can verify that this is bounded by 2. And if we calculate the successive approximation, and we can say that successive approximation is given by y naught t equal to 0, y 2 k minus 1 t equal to t square, y 2 k t equal to minus t square, that you can verify from this, and that you can easily calculate. Y 0 is given as 0, no problem. Y 1 you can calculate 0 plus t naught to t f of s 0 d of s, and you can say that this lying here here. So, here this can be written as t naught to t, and this is 2 t to s minus 4, this is 0 upon s ds. If you simplify, your y1 is coming out to be s square. So, y1 t is coming out as t square, and similarly you can find out y2 and so on, and you can see that your approximations are coming like this. But if you observe here, your odd terms, odd sequence will converging to t square is nothing but t square, and even is giving minus t square. So, it means that there is a successive approximation alternate between t square and minus t square and do not converge, and since the function f t y is continuous and bounded, therefore, by theorem 2 we have the existence of solution. So, existence of solution is given, and not only this, f is monotonically non increasing in y, that I am also leaving on you please verify. Then we can say that corollary 11 gives the assurance of existence of unique solution. So, it means that here in this particular problem, your approximation successive approximation solutions does not converge, but it has a unique solution. So, we can observe the following thing based on this example, that assurance of merely existence of solution does not require Lipschitz condition, that is guaranteed by this, that y to the power 2 by 3. Here if you look at this problem, here this does not satisfy the Lipschitz condition, but still it has a solution. So, assurance of merely existence of solution does not require Lipschitz condition, only continuity of f is required in y. Second, approximation do not converge, but still we have a unique solution, that is done by previous example. Thus, continuity of f and uniqueness of solution do not imply the convergence of approximate solution. In this problem we have continuous function, and here we also assume that solution is also unique, but still we do not have convergence of approximate solution, because approximate solution may not converge to a limit point. So, this means that uniqueness result and convergence of successive approximation are two different independent phenomena. So, that is this last two conclusion are based on the example given here, and the first example first conclusion is based on this example, that here uniqueness does not require Lipschitz condition, existence does not require Lipschitz condition, only continuity is also sufficient. So, with this we end our lecture. So, in this lecture what we have done, we have discussed the initial value problem and discussed the condition required for existence and uniqueness of the solution of the initial value problem. So, we will continue in next lecture. Thank you very much for this.